Hi. Wow, it's loud. First time on stage, really exciting. So first of all, I'm really excited to be here. First Java Summit in Israel, hopefully the first out of many. And today I'm going to talk about Amazon Lambdas cold start, specifically for Java-based Lambdas. And we're going to talk about how we can reduce the cold start, runtime latency, and save time and money. Because time is money, and money is something that we usually don't have. As developers, we want to write application and code that is robust, maintainable, scalable, and all the other buzzwords that we usually hear. But the thing is that we also want it to be cost-effective. In a utopian world, we have one server that costs $5 and can process bajillion requests in 100 milliseconds. Unfortunately, it's not the use case, but we're going to talk about it. So, hi, my name is Itai, 33 years old, tech lead at Joonko. I live in Tel Aviv with my wife, Mor, my dog, Leah, and the lord of the house, Snuggles, aka Snuggy. Beside coding, I love listening to music and play the drums. My neighbors hates me. So, what we're going to talk about today. So, what exactly is cold start? Specifically for Amazon Lambdas, Java-based Lambdas. How we can reduce the cold start and runtime latency. We're going to talk about 4 optimization points. The Amazon SDK version 2, the tiered compilation, execution context, and finally memory optimization. We're going to talk about best practices for Java-based Lambdas, and of course, frameworks. So what do we do at Joonko before we start? First of all, this is Joonko, the first woman who ever climbed the Everest, and specifically in Joonko, we're in a startup in the HR tech or the HRM. It's a booming market in the last 5 years, and we're offering a unique software as a service solution that connects between great and underrepresented talent and companies that are looking to be more inclusive. So raise your hand if you have heard the term serverless computing or serverless in general. Okay, for those of you who haven't, and you have any questions about it later, feel free to ask me about it. But the thing is that serverless is a cloud-native development model that allows developers to build and run applications on the cloud without actually need to maintain servers, which is great. Now, first of all, it's really cost-effective. The Lambdas in Amazon, you per use, you per millisecond that you actually use in the Lambda. Really easy to scale because everything is managed in the cloud, and it reduces the needs, to maintain servers. And it gives us the option to focus more about writing code. Now, I'm not going to argue that serverless is the best solution for everything, because it's not. And specifically for Joonko, it works for us really well in our event-driven architecture. So Amazon Lambda is usually referred to as function as a service. And specifically in Amazon, it can be triggered by almost any component inside Amazon. HTTP request using the API gateway, simple queue service with the events, and you have concurrency, which handles all the scaling that you need. And of course, again, you pay per use, which was really important and going to lead us throughout the talk. So why did we choose serverless at Joonko? First of all, the daily data collection that we do at Joonko, for all of our clients, once a day, we take all the candidates and the jobs that the company has to offer using their applicant tracking system, which is the interview process system. We collect it daily. And the thing is, it takes about 2 hours to go through all of our clients and collect the data. And we don't need servers up and running 24/7, right? 2 hours, 22 hours a day, we don't need the rest of them. We don't use that. So it's a real money saving for processing data that we need and pay exactly for what we need. And modularity. The thing is, this is a glance of one point of our architecture, and you can see all the Lambdas inside. And let's say that we have one client that we need to, for all the candidates of the client, to download the resume and parse it, for example. Then we can create a single Lambda, small Lambda, that its sole purpose is to analyze the resume. And the thing is that it's really easy to just redirect the event for a specific set of clients through that specific Lambda, process the event, and move forward. Really modular, really dynamics, and gives us exactly what we need at Joonko. So what is cold start? So the initialization of the Lambda when it's first triggered has 4 steps. The first one, the instance is being created inside a container, somewhere around the region that you chose. And the code is being downloaded from some sort of internal storage in Amazon. Now, the second step is the new execution environment is being created. Okay, the JVM is being created inside the instance with memory and runtime configuration and any other additional configuration that you set when you created the Lambda in the Lambda console. Now, the third step is initialization of the handler code. So the handler class that if you ever worked with Lambda, and I will show you it in a minute, but the handler class is being loaded, but we don't execute the code yet. Everything outside the handler function, the static variables, class variables, any other dependencies that are in the class are being loaded before we actually execute the code. Now the thing is that for those 3 steps, we're not paying, which is great. And the fourth step, which we obviously pay, is the execution of the actual code of the handler. So once we finish running the code, just whatever you need, we'll give you the response you need or send a new event to different Lambda, then the environment freezes. The reason that it happens is because Amazon wants to improve the resource management of the Lambda. We don't want for any instance or any trigger of the Lambda to create a new instance, a new JVM, new configuration, everything, and then execute the code. It will be a lot of time. So when we execute the code, we want to reuse everything we can. That is the reason why the first event is really, really slow, because everything is initialized, what is called a cold start. And the second and, well, later on events are way faster. They're called the warm start. During the talk, those 4 steps will guide us through everything we're going to talk about, and specifically the optimization points. Now, why do we hate cold start? Well, it's pretty obvious, first of all. It's very slow, and we don't like slow things, right? We want things to be fast. It's a killer of performance. Think about a web app or a mobile gaming app that requires a low latency, and the first user comes, good morning, open the app, send a request, and it waits. It's not a good user experience. And the thing is that when you want to scale up and more instances are being created, the entire process of the initialization happens again, and you have a cold start. And again, it's slow, and we don't like that. Specifically in Java, unfortunately, it's way slower than other programming languages, at least for the moment, in specific environments. But we need to stay positive. The thing is that, first of all, it used to be way slower than it is today. And there are a lot of smart people in Amazon that keep working on it to make it better and faster. So when in Joonko 4 years ago, I had no clue about serverless. It was my first time ever encountering Amazon and the concept of serverless. I used to work with a huge, giant monolith before, and it was amazing. It's a great experience to just learn new technology, the things you don't know. And the first use case that I encountered I need to develop in Joonko was the mailer. Well, as it says, it sends mails, specifically to candidates. And it looks something like that. And this is the use case that is going to lead us through most of the talk. So, the simple queue service, an event, triggers the Lambda. The Lambda connects to the MySQL database to get the template of the email. If needed, it will go to simple storage service to download an attachment, wrap everything together nicely, and send it to Gmail API to send an email to, well, someone. Pretty straightforward. Now, first thing, it was really, really slow for the first time. Send an email, it takes a while till you get the email. That is annoying. And we had 2 use cases. The first one, we had to target specific candidates and send them campaign emails. Now, when you send a campaign email, like any advertisement email, you don't really care. It will take 1 minute or 2 minutes to send the email, right? Because eventually someone will get it and read it, and it's fine. And a while ago, we started to have a second use case. We had a customer-facing application, some sort of dashboard to our clients, and we had a verification email. Now think about the use case when you go, you type your email inside the website, then you have a pop-up, nice one, purple one, that says, go to check your inbox, the verification code awaits. Then you go to inbox and you wait, and you don't get it. And it's really slow, and it's a bad user experience, right? Then you click send it again because I didn't get it, and then you get 2 emails. That is really annoying. Back in the day, we just started at Joonko. We were 2 developers, some sort of MVP phase. We had lots of more important things to do than figure it out why those emails are being so slow. So we didn't do that. But a while ago, we had time to do that. So first of all, the setting of the Lambda is where we used Linux 1, Java 8, don't hate me for that, and 512 megabytes of memory. So a while ago, I decided that I want to go down the rabbit hole and figure it out because we got some time. So it's a quick Lambda optimization, 20 minutes adventure in and out. And if you ever seen Rick and Morty, you know how it ends. But in our case, we'll be fine. So we need to talk about how can we measure the cold start, right? So the thing is, if you go to your Lambda console, you can go to the test section and just, well, test your Lambda. You can choose any type of input you want. You have lots of templates of the API gateway, SQS events, event bridge, whatever you want, you can use it inside. And the most cool thing about it is that when you test it, you can actually see the results of how long it took the Lambda to initialize the first 3 steps to run, and how long it took to execute the code, which we actually pay for. Now I ran my Lambda for the first time, and I see that the initialization duration took 900 milliseconds, which again, we're not paying for. But those are the first 3 steps. And the actual run duration, the runtime duration was 20 seconds. Well, that is a lot. Think about it. 21 seconds to send the first email. In our use case of the verification code, well, it's a really, really bad user experience. Think about it, you wait like 18 seconds probably for the email. Well, it's bad. So first of all, seeing this, I was pissed. 21 seconds, I can take out my phone and send an email faster than that. Not really helpful. And before starting to optimize it and figure out what's going on, I did the one most important thing I could ever do, and every sane developer would probably do in my place. I made a list of things that I can do in 21 seconds. So I can watch a Saint Bolt regular world record for 200 millimeters run and still have time to take this picture. I can watch Ricky Jackson do the same, a bit slower. I can watch my hands COVID style. I can Google things that can be done in 20 seconds because 21 seconds didn't lead to such good results. And you can listen to me rant about it a lot. And I probably have some few seconds to spare. So back to reality. I ran the event again. And it took 35 milliseconds. Now I ran it for 100 times more just to see how it's going on. And the average was 25 milliseconds. It means that for the amount of time it took us to send the first email, which is 21 seconds, I can send roughly 800 emails, which is a lot. Well, I'm not expecting our Lambda to initialize and start in 25 or 100 milliseconds. I wish. But since we want to be cost effective, well, we want to optimize that. And we can do better. And this leads us to our first optimization point. Sorry, before that. We need to take a look inside the Lambda to figure out what's going on. Before we start optimizing, we need to figure out what's going on during our runtime. And you can use X-Ray. X-Ray is a great tool that Amazon provides that gives us the option to actually look inside the Lambda at runtime and figure, well, what's going on. It's great for finding bottlenecks. In our case, it's really important because it's really, really slow. So you can go to your Lambda configuration and just go to the monitoring section and enable active tracing. The next thing you have to do is you just add to Gradle, Maven, whatever dependency management you use, add the Amazon SDK of X-Ray. It can cover MySQL, Postgres, Dynamo, whatever you need, and it gives you the option to, well, execute specific segments of the code and track them during the runtime. It looks something like that for the first event. You can see the entire runtime, what's going on, step by step, and how long it took. Now, if we zoom in, we can see that the MySQL connection took 11.5 seconds, which is almost half of the runtime, which is crazy, right? And inside that, you can see that the Amazon KMS took 4 seconds because we decrypt the database password, which is, well, a lot. And I tried to figure out, first of all, why it takes 4 seconds to just decrypt the password, right? It's really, really slow. And this leads us to the first optimization point, the Amazon SDK version 2. So first of all, when we started at Joonko, version 2 didn't exist. It was only version 1. And when it came out, we didn't just rush to upgrade everything because, it takes time to upgrade to a major version. Now, why should you do that? First of all, we need to remove redundant dependencies. Now it's obvious, right? You don't just put dependencies whatever you want. You need to keep that in mind. But it usually happens that you have some dependency that you don't really remember that you don't use, and you don't remove that. And if things are being loaded, well, it takes more time in the initialization process. Now, the number of classes that are being loaded actually matter for the initialization process, because the JVM lazy loads lots of classes and it impacts the initialization process. So, well, remove whatever you can. And next time that you use a class that has only one, you have like create one interface for one class implementation, and you don't need it because you don't have any other implementations, but you do it because it's the right thing to do. Well, specifically in Lambdas, don't do that, because it will slow you down. And I found that the jar size doesn't really matter. The package size doesn't really matter as expected, because I would think that if my package is 30 megabytes instead of 50, it will be faster. It doesn't really affect much. So the thing is that, first of all, Amazon SDK version 2 was created with Lambda in mind. It was created a lot after Lambda was introduced to the world, and they made it more modular. So the version 1, you had one SDK that you used that contained all the clients, the DynamoDB, the KMS, the simple storage service, everything you wanted in one place. And it loads, well, lots of redundant dependencies that we don't actually use. Now in V2, you can just choose specific dependencies such as KMS and just import that. It's a bit bigger in package terms, but the number of classes that will be loaded are less, and it makes everything faster. And the most cool thing is that we can pick the HTTP client that we want to use. Now, by default, the Amazon SDK version 2 uses Apache or Netty for HTTP requests between the services. And unless you're making like, I don't know, 50 or 60 async requests of HTTP inside your Lambda, you don't really need that. Because just make one HTTP request to the service and it should be really, really simple. So instead of using Netty or Apache, you exclude them and use the URL connection client, which is the most lightweight and simple HTTP library that exists. So when we initialize the simple storage service client, for example, you can just use the builder to set the HTTP client, whatever you choose. By the way, if you want to use Apache or Netty, do that. The thing is with that builder is that, well, we specify exactly what is going on. If you can specify, if you know the region, you can use it, get it from the environment variable, or specifically from enum if you're working on a single region, and specify it in the builder. If you won't do that, it will go to auto discovery and start looking for the right region or the right credential provider. And this takes time, which we don't have. So if you have the region, and you do have, set it. And the credentials provider, well, specifically in Lambda, it's always in the environment variables, unless you specify otherwise. And by the permissions and setting of the Lambda, it's already there and you don't see it in the console. But you can just direct the client to go and seek for the credentials there. Because if you won't do that, it will go start looking for internals files and stuff like that, and it's a waste of time. And if you're working in a single region, you can also configure the endpoint for the specific client that you are working on, in this case, simple storage service. So I changed everything to Amazon V2. Factor everything, deleted all packages, and I wanted to see how much it impact. And the results are 60% improvement. Well, if you can see that the initialization duration is now a bit lower, it's 800 milliseconds, and the build duration is 17 seconds. I must say I expected it to be a bit faster. But still, 16% is improvement, 3 seconds. It's good. We're in the right direction. And the thing is that the version 2, if you haven't upgraded it, it becomes a standard to use it. And in my opinion, at least code-wise, it's, well, cleaner. So we're in the right direction, and this leads me to our second optimization point, the tiered compilation. Now, have you ever heard the term just-in-time compilers? If not, you have lots of reading to do. It might be a bit boring. But the thing is that in runtime, the just-in-time compilers are responsible for the optimization of our code at runtime, which is really cool. Now, as we know, your source code, the Java file, is being used by the compiler, and then it's transferred to bytecode at compile time. But at runtime, the just-in-time compilers take the pieces of the bytecode, optimize it, and transfer it to native execution code, machine code. Now, you target specific functions that you have, and just optimize it. Now, we have two types of just-in-time compilers. We have the C1, and the C2. C1 was originally designed for clients, desktop applications, for fast startup times, because usually those desktops have CPU with one core, less memory, and well, fast startup time is what we need. And the C2 was made for servers. Well, it takes more time to peak performance, but in the long run, it will observe your code longer, gather lots of data and profiling, and will make it run faster. And it takes more memory, obviously. Before Java 8, you had to choose one, and after Java 8, tiered compilation was introduced, which is the mix of the two of them. So as you can see, we start with level 0, which is the interpreter, and we go to level 1, which is the C1 with the profiling, without profiling, level 2, C1 basic profiling, level 3, full profiling of the C1, and finally level 4, which is C2. Now, the typical compilation sequence, we start for level 0, go to level 3, which is, again, C1 with full profiling, and finally to C2 after a while. Not all the compilation sequences go like that. There are many use cases which change. But since we're using Lambda and we want fast startup time, well, we're going to use C1. Well, it's faster. But if you have Lambda that somehow runs, the instance runs for a really, really long time, which is usually doesn't happen, try C2. See if it works for you. But the benchmarks and the tests that I did and everything that you see that C1 is the right one for you. So it's really, really simple to do. You go to the environment variables, the Java tool option, and you add those two flags. We're going to use C1 without profiling because it's an overhead and we don't want that. So we stop the tiered compilation at level 1. First flag, enable the tiered compilation. Second flag, stop it at the first level. So I did that. It took around 15 seconds. And I ran the test again. 40% improvement from the first event. Well, now you can see that the initialization duration is 700 milliseconds and the build duration is 12 seconds, which is actual runtime. So around 30 seconds to execute the email. Well, it's faster, way faster than 21 seconds, but it's still not enough. But again, well, it's an improvement. So why not? So the third point of the optimization, before we get to that, few points about the initialization step of the handler, the third step. So first of all, the amount of memory that we allocate to the Lambda determines the amount of virtual CPU that the Lambda gets. More memory, more CPU. And the thing is that everything outside the handler request function, when it's being loaded on the first 3 steps of the Lambda initialization, gets a boost of CPU because Amazon wants the instance to create fast and initialize as fast as possible. And the thing is that we can use it in our favor. Which leads me to our third optimization point, the execution context. Now, what if we could do all the heavy lifting outside the handle request function? Think about when we took a look at the X-ray, it took 11 seconds to initialize the MySQL connection. That is slow. So if you can use the CPU boost in our favor to initialize the connection faster, that would be great, right? So this is a snapshot of one of our handlers. And, well, pretty straightforward. We get an SQS event and just process it. Now, I decided to take the database connection and the initialization of the Gmail service that contains other clients inside and just put it in the constructor. So if you use static variables or variables that you initialize using the constructor in class level, they will be initialized before the handle request function will be executed, which means it's part of the third step, which is the initialization process, which gets a CPU boost, which should be great, right? And it looks something like that. You can see the actual separation between the handle request function and everything that's inside the execution context. And again, those things are going to be reused because we want to improve our resource management inside the container. Now, the resources provider I'm going to talk about later, so don't worry about it. So, as you can see, we have the container, the JVM inside, and the Lambda, and everything wrapped around in the code, which makes the execution context so special. So I took everything out, as I showed you, and I ran it again. And it led to 71% improvement of the first event. So now, you can see the initialization duration is 3 seconds. Well, it makes sense. We moved all the heavy lifting outside the handle request function. Now it's part of initialization step. It gets a CPU boost, and it's part of initialization, and we're not paying for that. And the runtime duration, the build duration, is 3 seconds. It means that it took us, first of all, 6 seconds instead of 21 to send the first email, which is amazing, right? And we're not paying for half of the time that it took us to run. So it's really good. But I still think that we can do better. And again, well, 71% improvement. If the clicker works. Weren't my GIF. Anyway, so the main takeaways from this part is, first of all, everything outside of the handle request function is being initialized and gets a CPU boost, okay? CPU boost for the win. Use it in your favor. Now, the thing is that you have the 10-second rule. If the initialization process took more than 10 seconds, Amazon will consider the process dead and will kill your Lambda, and we don't want that. Anyway, if your initialization process takes more than 10 seconds, you probably have an issue. So figure it out, but don't put everything out there. So if you have something that the entire Lambda used and it's really heavy, do that. Otherwise, try to lazy load it. And we're not paying for initialization time, which is great, right? It works again. So memory optimization, that is our fourth and final optimization point. So memory is like a silver bullet solution, right? You have a slow server, increase the memory, everything will be blazing fast. And the thing is that it comes with a cost. You can allocate 5 gigabytes of memory to your Lambda and it will be faster. Initialization will be faster, everything will be faster. But again, it costs more money. The more memory, the more money you pay. And we want to be cost effective. So before I just explode my Lambda with a bajillion gigabytes of memory and it improves everything, I decided to figure out what is the best setting of memory that I can use. So I found the Amazon Lambda power tuning tool, which is an open source tool that you can find it anywhere in the Amazon documentation. Those guys really like it and it's a really good one. That it creates a state machine with step functions to optimize our Lambda. It will test the Lambda on various memory configuration and see what is the best solution for us. Now, you can use Terraform or any other infrastructure as code to deploy it. It takes like a few minutes, really simple, and it's up and running. Now, when you want to execute it, well, you have a simple configuration. First one, you need to point it to the right Lambda, right? In our case, the mailer. And you have the power values, which is a set of memory configurations that we want to test. In our case, from 512 megabytes of memory to 2,500 megabytes of memory. Each and every set of memory configuration will be tested for the number of iterations that you set. In my case, 10. I didn't want to spam the inbox, and well, I did it once, but it was still good enough. You have the payload, which is the event, the body of the event, and the strategy. You have 3 types of strategies. Cost, which will optimize for lower cost, speed, for faster time, execution time, and a balanced solution, which is a balance between them. I choose speed for the sake of the example, and I want to see how fast can you go. So it gives you this solution, this chart. Now, the red line indicates the number of time in milliseconds in average it took all the iteration to run for the memory configuration. And the blue line indicates the cost. Now, it gives us all the data that we need to decide what is going on. Now, as you can see, 1 gigabyte of memory is the best cost. And 1,850 megabytes of memory is the best runtime. I decided to go with 1 gigabyte of memory to see if it's enough and to cut the cost and see if it will run well. So I just set the memory configuration to 1 gigabyte of memory and ran the Lambda again. 85% improvement for the first event. Now the initialization duration takes 2.2 seconds, which we're not paying for, which is great. And the actual runtime, the build duration, is 1.1 seconds. It took us 3.3 seconds to send the actual first email. Okay, so first time, 21 seconds, really slow. 3.3 seconds, really fast. Think about the verification process example. You insert your email, you get the verification code. By the time you go to your email tab, the email is already there. Really great user experience compared to the 21 seconds that we had before. And, well, that is lovely. So now that we have the numbers, we can see that in terms of cold start, the memory configuration of 512 megabytes, it took the runtime of 3.2 seconds, and if we compare it to 1 million requests, it's $27. Now, for 1 gigabyte of memory, the runtime is 1.1 seconds, and the price is $18. Well, it means that we can run faster and pay less. But you can test it also on the average and not only on the cold start, but you can see that sometimes with the right memory configuration, you can pay less and run faster, which is a no-brainer, right? Now, if you want a faster cold start or runtime for the first event, you can use the 2 gigabytes of memory. And it will cost you, well, the same as the 512. And that is fine. It is okay to pay more money for more resources. Well, want to be cost effective, those are the numbers, do your math, it's okay. But when you have the numbers, it's really easy to make a decision. So enough about optimization points. We've been to 4, I think it's enough. And we're going to talk about other Java Lambdas practices. So, what if the Lambda could just stay warm, up and running all the time? Well, we'll probably call it an EC2 or a server instead. But the thing is that a while ago, Amazon introduced the provision concurrency. It gives us the option to just select a number of instances that you want and keep them up and running all the time. Well, if they're up and running all the time, well, it helps to reduce the impact of cold start. Every instance that you have, well, will serve a new request and it will be up and running, which is great. It keeps them warm, everything is good. Well, of course, it comes with an additional cost. The thing is that we pay for the number of instances and the runtime. And of course, the memory that they're using, and of course, the actual execution of the Lambda. So in our use case, I try to create few instances to see how it's going. By the way, if you didn't understand the reference of the absolutely nothing, go watch Rush Hour 1 with Chris Tucker and Jackie Chan, but it doesn't really matter. It's a good thing. And you go to the Lambda settings, you go to the provision concurrency, and you set the number of instances you want. 1, 2, 100, whatever you want. A few seconds, and it will be initialized. That's all too much. Now, when they're up and running, well, they serve any request that will come faster than anything else because it doesn't have a cold start, because it's already warm. Now, the thing is that in Joonko, we don't need that because it takes us 2 hours a day, well, to collect all the data that we need. So I don't want to pay, and I don't want to handle those instances the entire day. I want them only for 2 hours. So you can use the application auto-scaling. So the thing is, with a really simple command line configuration, you can set the scaling of those instances, of the provision concurrency instances, based on utilization percentage and, well, time. You can use a cron expression to set it to start running from 7 a.m. to 9 a.m., for example, which is great for us. And you can just control the capacity. For example, if you have the minimum capacity, you can say 50, and the maximum capacity of 500. And if you have a traffic burst, more and more instances will be created in runtime to serve your application, which is really, really good for applications that require low latency, or a web app, or a mobile game that requires a really fast response. So again, it comes with a cost, but it's still a great use if you need a fast response time. We use it in Joonko for a few use cases, and it's really helpful. Now, I promised you that I will talk about the resources provider. And the thing is that with Joonko, we decided that we don't want to use a framework, but we still need a way to reuse all the dependencies that we have. The thing is, we created the resources provider, which is a singleton class that contains all the resources that the Lambda needs. Database connections, DynamoDB, simple KMS clients, whatever you want. And the thing is that, well, reuse is the key. So even if we don't initialize the database connection outside of the handle request function as we've seen before, well, we still want to reuse it, right? Think about the use case that you trigger the Lambda and every time it initializes a new connection to the database. That is really slow. It's not good. So if you can reuse that, everything will be blazing fast on the second execution of the Lambda, even if we didn't initialize the connection in the first place. Well, we can still reuse it. And it looks something like that. Well, singleton pattern, pretty straightforward, nothing too messy. And we have the mail types database connection, which is the email templates that we use, and the Gmail service, which it contains all the clients and the HTTP invocation to Gmail. Now, at the getter function, it's well, all the magic happens. So when we create the, sorry for that. No, just keep talking. Okay. So in the getter function, we have the mail type database, for example. Okay, and we initialize it only one time, and we use it for the entire runtime of the Lambda. Now the thing is that we control the dependencies of those classes. You can do whatever you want. Any logic that you want, you can create each and every connection from every time that you invoke the Lambda, and you can reuse everything again. Well, I know it's not as fun and nice as a Spring dependency injection, but it gives us the control that we need when we manage our resources. And we reuse all those resources, everything will be faster and will cost us less money. So, you can't have a talk on Java and specific Lambdas without mentioning a few frameworks. Now, how many of you use Spring at work? Raise your hand. Leave your hand up if you're using Spring with Lambda. Figured. Okay, talk about it. So, the thing is that, well, first of all, I really love Spring. Don't get me wrong. But the thing is that for Lambda, it's probably an overkill, in my opinion, because it's really, really heavy. Loads bajillion of classes when it initializes, and we already know it's not a good thing, and it slows down the initialization of the Lambda. It relies heavily on reflection, which also slows us down, and, well, we don't really use everything Spring has to offer on the short lifespan of the Lambda, usually. So, before you get mad, I'm not going to compare Spring and Dagger 2, because they're not comparable, they're not the same. But in terms of dependency injection, well, we can talk about it. So Spring dependency injection works at runtime, which is really great, but in Lambda perspective, it's really slow, and it's not really good for us. Now, if you really want to use a dependency injection framework, well, think about Dagger 2. Dagger 2 does all the heavy lifting and all the dependency injection at compile time. Means that at runtime, nothing really happens because everything is already done. And it's way faster. And everything is done, probably the same, looks the same, annotation is everything that you have in Spring, but it's faster. So if you are considering to using a dependency injection framework, think about Dagger 2 before running to implement Spring, specifically when you're using Lambda. Now lately, there have been some rising stars in the Java world in terms of frameworks. So first of all, I know that when I started to talk about Lambda cold start, some of you might think, why don't you use GraalVM? It will kill the cold start, it will be blazing fast. First of all, you're right. But it's for a different talk. And the thing is that, first of all, if you don't know GraalVM, it's a VM that based on the hotspot in OpenGDK. It creates a native execution environment. It has a really cool execution mode called ahead of time compilation. All the heavy lifting, everything is done at compile time. It takes a while to build your executable jar environment. And when you deploy the native image of the GraalVM, the startup time is really, really fast because everything is done at compile time. And the memory footprint is really, really low, which is great for Lambdas, but it has its trade-off. The build time is really long, it doesn't handle well with reflection. Well, you need to read about it, but take a look because it's really, really cool. And the thing is that lately I've got to know Micronaut and Quarkus. Well, they're both open source frameworks, and they have also the compilation ahead of time execution mode, and they work really well with GraalVM. So if you still want to use a framework, well, I'm not saying don't use Spring, but if you still want to use a framework with Lambda, use Quarkus or Micronaut. The startup time is really fast, the memory footprint is really low, which is exactly what we need when we're using a Lambda. Now, the thing is, first of all, if you want to hear more about Quarkus, there is a lecture, I think, in 2 hours that you can go read. Go see Sebastian talking about why Quarkus is the best thing. I haven't still figured out which one of them is better, but, well, it's only my opinion. But the thing is, go read about it. If you want to use a framework, why not? One of them might be the right solution for you. So, let's wrap everything up. The main takeaways from this talk. First, we started with a really, really slow email event, which took 21 seconds. I was pissed off, figured out what to do, and we started the first optimization point of the Amazon SDK version 2. It's way more modular. You can use the HTTP client, and you avoid auto discovery by configuring the client builder properly. It gave us 70% improvement. Then we moved to the tiered compilation. I blabbered a bit about just-in-time compilers. Then we choose C1. You set the environment variable, pretty straightforward, pretty simple, and gave us 40% improvement. Then the execution context. Do all the heavy lifting or most of the heavy lifting outside the handle request function. Database connections, whatever you need. You get a CPU boost, use it in your favor. You are not paying for that and it's still faster. This gave us 71% improvement. And the final optimization point was the memory optimization using the Amazon Lambda power tuning tool, which gave us 85% improvement. Really easy to deploy, and it helps us to find the sweet spot of the memory configuration between runtime and cost, which is great when we talk in terms of Amazon Lambdas. Provision concurrency. Keep Lambdas up and instances up and running and warm. Reduces the cold start. Everything will be way faster for specific instances. Well, it comes with the initial cost, and it's great for application that requires low latency, mobile games, web apps, whatever you want to use it. And a small bonus. If you're still using Java.IL like we do, and you still haven't upgraded to Linux 2, well, go do that. It gives a bit of an edge. And the Amazon solution architects. If you haven't met them, schedule a 30-minute call. I promise you it will be worth your while. Everyone that I encountered and did it multiple times had vast knowledge on everything that comes to Amazon. And they're really helpful, and they have fresh perspective on whatever you're doing. So go do that. The thing is that most of the things that we talk are specifically for Amazon Web Services, right? But I think that at least some of them can be applied in any other cloud provider. I haven't tried that, but you can go look it out. I'm sure that the memory optimization and part of the execution context is probably the same. And well, also the tiered compilation. You can do it without any effort. So the thing is that even if your application is not tailor-made for a low latency use case, well, you can still use at least some of those optimization points or the other features that Amazon has to offer because, well, it's really easy and it's really fast. And it's a no-brainer to use them because it will reduce your cost and will improve the user experience, or at least the runtime in average of your Lambdas. So if you can do that, well, why not? So before we finish, we're creating a tech lead forum sponsored by Joonko. So if you are passionate about code, design, love pizza and beer, and not generally about Java, but anything, contact me for more details. I'm Itai. This is my email, LinkedIn. Thank you very much.